should we start? So today I'm going to make a total digression from what we've been doing so far, because I thought the order of that I was doing things was not quite right. Namely, if I want to talk about integration, I don't first, to begin with, start talking about, for your first exposure to integration, I don't start talking about integration over a space of infinite measure and the two Lebesgue integrals. Right? But the measure theoretic integration, so that I don't do, that do an infinite measure. That is not the place one should start. Before this one, you should at least understand the finite. So let me repeat. Are more coming, or are you alone? Okay. So I was trying to say that this is going to be a kind of detour from what we've been doing so far. And I was drawing an analogy with saying what we were going to do was to discuss integration over the two Lebesgue or measure theoretic integration over infinite measure spaces. Okay. But in measure theory, before you do that, you first understand. Before that, you will at least do Lebesgue integration on 0, 1, on finite measure spaces. So you don't have the problems of infinite measure. So that at least constant functions are integrable. But as a precursor to that, the first exposure you have to integration is Riemann integration. Right? Which is where you learn how to integrate continuous functions. And all this thing about the measure theoretic certainties come on the second course. So the analog of that is the infinite measure spaces I'm talking about corresponds to looking at weights on measure spaces and doing their associated L2 spaces, which I was going to get into. So before that, if you want to do like integration on Lebesgue integration on finite measure spaces, we should talk about at least normal states on monomial algebras. But before that, the analog of the Riemann integration, how you treat continuous functions. So the analog for that is to deal with just states on C-star algebras. C-star algebras are non-commutative continuous function spaces. Right? In that a non so let me back up. See, we've been talking about one-Neumann algebras, also called W-star algebras. And a precursor to that is C-star algebras. And in both of these, this also I've said in the past, but it doesn't hurt to repeat. In both of these, there's an abstract definition and a concrete definition. There's an abstract definition of a group which says a group is a set which admits a binary operation which satisfies conditions 1, 2, 3, 4. anything which satisfies that is a group. And you prove theorems in generality about such abstract groups, and then you can apply them to any group at all that you look at, and then you'll be able to do work with groups comfortably. But then you realize that groups are really, if you're talking about finite groups, then a concrete definition of a finite group could be just a subgroup of the permutation group. And then you prove a theorem that says that every group is isomorphic to a subgroup of the permutation group. So that usually in many of the mathematical theories, one has a concrete definition and an abstract definition which has the advantage that it is not tied down to some background noise which the other thing comes equipped with. You don't need all that to just study this in generality. So, the same way, a C-star algebra, so see both of them have this concrete abstract definition and concrete definition. And then one can talk about the category of these objects. There is a category where these guys are the objects, and there is the natural notion of what the morphisms are. And then you prove that this concrete thing that you define is an object in this general category you're talking about. Whereas this abstract thing is just any object in that category. And then you prove this Cayley's theorem analog, where you prove that any abstract such object is isomorphic in that category to the concrete one that you first started off with. So you need this, and very often the concrete definition gives you a better initial understanding, but the abstract one has its advantages because it doesn't tie you down to, I don't always have to talk about the permutation group, I get to talk about a group in general. So similarly, in C-star and von Neumann algebras, in operator algebras, usually the concrete definition is that these things are subalgebras of B of H for some Hilbert space, which are self-adjoint usually, and which are closed in some appropriate topology. So that is a concrete definition, but that unnecessarily ties you down to that Hilbert space. The abstract approach says no, a von Neumann algebra deserves to be looked at on its own right without being tied down to that Hilbert space. There can be other pictures for that von Neumann algebra. For example, if you take the permutation group on 3 symbols, so there is one abstract, the actual definition of the permutation group is that as permutations that 3-element set. And another useful way to think of this as the group which permutes the coordinates over 3-dimensional space. So you're defining a representation of the group, meaning typically in all these categories, the objects will be tied down to some vector spaces of some kind. The morphisms will be linear transformations with appropriate continuity conditions. And you will prove that, and then you will prove what you mean by a representation, which is just a morphism in this category from the abstract one to the concrete one. And then the theorem, the Cayley theorem, would correspond to proving that any abstract such object admits faithful, meaning one-to-one representation, isomorphic, is isomorphic to the example of the concrete such object. Right? So, let me quickly recall these things for you. A C-star algebra, or let me do it reverse. I'll do one-hour algebra because that's what we started with. And then I'll get to C-star algebra, which is what I want to start with discussing today before getting back to one-hour algebra. Okay, what is one-hour algebra? The abstract definition see, the concrete definition was that it is for example, a WOT closed star subalgebra of a B of H. Huh? Yeah. Okay. The abstract definition will say it is two things. One, it is a unitl C-star algebra. There exists M as a Banach space, admits a pre-dual space. That means M is isomorphic to the dual space of this, as M is isomorphic to the space of continuous linear functionals on this. What this means is there exists Banach space M, such that M is isomorphic to the dual of M lower star. Right? So this is the abstract definition. And then, so we will want to prove that any such abstract thing is, and so what is the category? The category, the objects of the category will be such things, such abstract one-Neumann algebras. The morphisms of the category will be C-star algebra homomorphisms, that means star algebra homomorphisms. And having the pre-dual means, in fact, it turns out that this is the theorem, it follows that this thing is actually unique up to isomorphism, isometric isomorphism. So what that means is, in its dual space, there is a distinguished subspace, namely its pre-dual. And there is by the uniqueness, there is a canonical weak star topology that this M has, right, which is what we call sigma weak topology. And the morphisms now will be the star algebra homomorphisms which are continuous in the weak star topology on domain and range. Right? So this is a more complicated object than just a C-star algebra. So let's go to C-star algebras first. Abstract is, it is a Banach algebra by Banach algebra, you mean, of course, that there is a norm which is related to the product. It is sub-multiplicative, norm of AB less than or equal to norm A and norm B. So all that is built into the definition of Banach algebra. And two, so let us stay with unitl. We can look at non-unitl refinements later if we need. And two, there exists an involution, an adjoint operation. Adjoint operation which satisfies certain natural conditions. What is it? There is, it is product reversing, it is additive, it is conjugate linear, and it is involutive. That means you do it twice, you get back to where you started. Right? These four properties, algebraic properties you require. And finally, you want a relation between these two structures. They can't be completely incompatible. So you want the star structure to be satisfy a consistency condition with respect to the Banach space structure, with the norm structure. And so that is the so-called C star identity. Which is that this is true for all x. Then there is the abstract definition. And the concrete definition is it's a norm closed. Because I am saying Banach algebra, it must be complete in the norm. So I must have take a norm closed subspace of Banach space to have a Banach space. So I want a norm closed unitl star subalgebra of B of H. And now you have a category of C star algebras. The objects are such objects. And what would you think the morphisms are? The morphisms will be, there must be Banach algebra, there will be algebra homomorphisms, there will be star homomorphisms, and there is a norm also. They will be consistent with the norm, they will be continuous in the norm. But in fact, that comes for free. It's the theorem that if you have a star homomorphism between C star algebras, it always has norm less than or equal to 1. So automatically it satisfies the continuity condition. If it preserves the star and the algebraic structure, it is automatically contractive. And if it is 1-to-1, it is always isometric. So for you to say isomorphism, you just have to say there is a 1-to-1 star algebra homomorphism from such an object into such an object. That means into some B of H. So given a C star algebra A, you will be interested in what are called representations of A, by which you mean star homomorphism from A into some B of H. So the interest is on representations of C star algebra A is just a star homomorphism. And because I have demanded unitl, I will assume everywhere that it is unit preserving. It sends 1 to 1. Okay. But now, okay, so let me not make that first. See, it is a consequence of the C star identity that norm of x squared equals norm x the whole squared for self-adjoint x, if x is self-adjoint. That will mean that if you can bootstrap that thing. That will mean that norm of x power 4, which is norm of x squared, will be norm of x the whole power 4. And in general, norm of x power 2 power n will be norm of x the whole power 2 power n. And so, by the spectral mapping theorem, it follows that the spectral radius of x agrees with the norm of x. And that is the clue to this statement. If you now have a star algebra homomorphism, unitl algebra homomorphism from unitl star algebra homomorphism from a C star algebra into some other C star algebra, then I want to say that it is norm decreasing. In view of the C star identity, which is true in both domain and range, and because your homomorphism is star preserving, it is enough to prove that it decreases the norm for self-adjoint elements, because x star x is always self-adjoint. And when x is self-adjoint, so this says that the norm of x is always just the spectral radius of x. And you just have to observe that if you have a unitl algebra homomorphism, it will send invertible things to invertible things. Consequently, the spectrum of the image will be contained in the spectrum of the thing you started with. That means the spectral radius of pi of x will be less than or equal to spectral radius of x. And so that will prove that it is norm decreasing on self-adjoints. Okay, so all that was to say why it is enough to not impose continuity here, that comes for free. Okay, but now we want to prove this KD kind of theorem. We want to prove that every C star algebra admits a representation which is one-to-one, a faithful representation into Hilbert space. Now, if I want to stay with my hang-up about separable Hilbert spaces, then I will have to impose the condition that A is also separable. In order for me to really be able to realize A, to be able to say definitely that you can realize it on some B of H for separable H. Okay, so how does one do this? So we want to first say that there exists a representation, and so we want to say there exists a faithful representation. One-to-one. Faithful means one-to-one. Faithful means one-to-one. Yeah, kernel is trivial. Okay, so you go back to the simplest examples you know and see how you will prove the theorem there. And see what the examples are over there. The simplest example of a okay, and then in abstract There is a so-called Gelfand theory for discussing general commutative Banach algebras. When you apply that to commutative C-star algebras, there is a theorem which says that any unitl commutative C-star algebra if you say the commutative term C-star algebras, what is an example of this? It is a C of x. You take the soup norm on continuous functions on a compact Hausdorff space. Now, the unitl requirement will translate to saying that x is compact. If you don't impose the unitl condition, then the theorem is that such a C-star algebra will look like what one calls C0 of x, which is functions which vanish at infinity of a locally compact Hausdorff space. So, let us not worry about the non-unitl case. There is a if you want to study the real line or you want to study the unit circle, where if you remove one point, you will get the real line after topology. So let us stay with the unitl case. Okay, so here how does one construct examples of representations? For example, I talked about Lebesgue measure. So suppose we take x equals 0, 1. How do I construct a representation of C of 0, 1? That means, representation means I must first find a Hilbert space on which I must be able to make these fellows act as operators. So I want to find a natural way of getting into a Hilbert space starting from this setup. And what is the natural way to get a Hilbert space from here? What? Hilbert space. No. No, I want an example of a natural Hilbert space on which C01 acts. So what is the Hilbert space you're talking? I think what you were trying to say was there is a one-dimensional representation. That is, I take A's to be the complex numbers and take the representation as f going to f of half or any one point. But that example is kind of cheap because it doesn't reflect anything about the continuity, the structure of these continuous functions here. I want to be able to get to prove something like this. I must be able to get the essence of C01 in a general Hilbert space. What is the general Hilbert space which somehow contains the essence of the topology of the unit interval? So you take for example Lebesgue measure. And you look at f going to multiplication by f. By this I mean the operator of multiplication by f. And here the adjoint is complex conjugation. You can verify that the adjoint of MF is M of f bar. So this is a star algebra homomorphism of C01 on L201 mu. In this case, if you taken mu to be Lebesgue measure, then this is actually 1-to-1. What does that say? It says that if integral 0 to 1 of mod f xi squared equals 0 for all xi in L201, I want to say this implies f is 0. This will imply, if I take xi to be an indicator function, that integral over any set E of mod f squared is 0. I can take this to be any interval, a, b. For a, b sitting in say 0, 1. Now if f is not 0, it is continuous. So mod f must be non-zero somewhere. So in some neighborhood it must be strictly positive. And so if I choose this interval to be inside a place where the mod f is bigger than epsilon or something, then this thing will be bigger than or equal to epsilon squared times the measure of the length of that interval. So it cannot be 0. Right? So by this device, in this case you got lucky by finding one measure which was able to detect the non-vanishing of a continuous function. By just knowing that MF is non-zero for this one measure mu, actually I shouldn't call it MF, I should probably call this pi mu of f. I define a representation pi mu where pi mu of f is multiplication by f on L2 mu. In the example that we just discussed, we got lucky. We were able to find one measure mu, so that already pi mu was 1-to-1. And so this thing worked out fine. But a general commutative series algebra looks like some C of x. Suppose that x is the Hilbert cube, which is a countable product of unit intervals. Then what is such a measure you can hope to get? One measure which will detect all. So in general, you may not be able to detect one measure which will detect the non-vanishing of a function. But what you can hope to do is to identify enough measures. See, you take See what we know is that for any mu, for any measure mu on x, any finite, so let's say probability measure, finite measure, finite positive measure. Only with the finite measure, then Cx will act as multiplication operator. So for any finite positive measure mu, we have a representation pi mu. What we know is that pi mu is a star homomorphism. There exists pi mu. I won't repeat this whole thing, blah, blah, blah. And what we know is that norm of pi mu is less than or equal to 1. in fact equal to, because they are all unitary. We are looking at unitary representations. So every unitary representation will have norm equal to 1 as an operator. Okay. But pi mu by itself may not be enough to see the non-vanishing of all functions. So you take as many measures as you want. Why not take the following thing? You take the direct sum over all measures in M of x. By this I mean the measures on x. Take all positive measures, finite positive measures on x. For every such mu, I want to look at direction. Each pi mu is contractive. That means for any f, pi mu f will have norm less than or equal to norm f. So if we take a direct sum of a bunch of operators whose norm is uniformly bounded, the entire direct sum will be a bounded operator. Now this is an operator, this will be a map from Cx to direct sum over all mu of L2 mu, which is a massive Hilbert space. For every measure on x, you've constructed one Hilbert space, and you've taken direct sum of all of them. Since the measures are the dual of the continuous functions, for every, if f is non-zero by Hahn-Banach, there will be some measure mu such that pi mu such that mu will f will not be 0 mu almost everywhere, such that integral mod f squared d mu will be positive. Okay. If mod f squared is not 0, it is a non-zero vector, so there will be something in the dual space. In fact, you can choose something positive, such that that will detect that. So now you proved this theorem but in some very large Hilbert space. But we would like to do something slightly better. We'd like to do this for so suppose you can do the following thing. For each f in Cx, essentially using the argument that I mouthed a little time ago, I can find a measure suppose you find one measure mu f such that norm of pi mu f equal to the sup norm of f. Suppose you could do this. Now, if you knew that C of x was separable, then you can just choose a sequence Fn. And for each Fn, you take one mu n, which will do the right thing. And then you take the direct sum of all the pi mu n's. But that will send A to direct sum of L2 mu n. But the point is that the separability of Cx implies that L2 x mu is separable in fact you can find continuous functions which approximate any L2 function in the 2 norm. So if you find any dense subsequence of Cx, that will automatically be dense in L2 in the 2 norm. Right? So what this will give you is you take direct sum over n pi mu fn. This will be a representation and on separable Hilbert space, because this is going to act on direct sum of L2 x mu n. And a countable direct sum of separable spaces is separable. Sorry? No, some take some dense sequence in Cx. Right? So where this is, I should have said in Fn, dense in Cx. So this is how you will prove the theorem for C of x. You have shown that Cx admits a faithful representation on Hilbert space and on separable Hilbert space if Cx had been separable to start with. So the same device one wants to apply.
You have to prove that for all if we can give it by mu such that norm is equal.
You can find a
If such that norm pi u equals to norm n.
Yeah, but for a general A, so
For all if I have to get a mu n such that pi mu n equals to norm n.
you take his favorite example. That f is continuous on a compact space, so mod f will be maximum somewhere. Norm f is going to be equal to absolute value of f of x naught for some x naught. Take pi mu to be take mu sub f to be just a point mass at that point x naught. And then L2 of x mu will be just that one dimensional space. And pi mu will just represent it as that scalar value at x naught. So we need to do the same thing now in general. So I now start with the general C-star algebra. So I want to find representations of this. Right? I want to play the same kind of game that I did in Cx. Right? And so what you do is, and incidentally, this argument already contained a germ of something that is very important, that Cx actually can be thought of as a dense subspace of L2 x mu. L2 x mu may be thought of as the completion of Cx for the L2 norm. Okay, so So here, the crucial fact is, so we need something like measures over here. What singles out measures, the positive measures? I could have said probability measure here if you want. What singles out probability measures on C of X? Huh? But not, dual is also, why is it a probability measure? It's just a dual is just a finite complex measure. So how do you get positivity? You need the notion of a positive measure. For a C star algebra, what is the analog of a positive measure? How do you describe the notion of a positive measure purely by viewing mu as a linear function on something? Right? So to say that mu is positive is the same as saying that the integral of every positive function is positive. Then the measure cannot have any negative part or anything. A priori it will be a complex part, a complex thing, but then you decompose and so on. And you can see that if the measure on integral of any positive function is positive, then the measure must be positive. This uses that Hahn-Banach thing, so I don't want to go into this digression now. So we want to look at, so the analog of positive measures is to look at, so I want to look at phi in A star which is positive. That means I want phi to map every positive element of A, which by definition is something that looks like that, to something positive, non-negative, for all x. Right? So such a thing is a positive function. And you, okay. So then one can ask the question, how do you know that such a positive function exists on a C-star algebra? So let me go back and just do one, let me first kind of assume it is positive and then do something for you, and then I come back to proving that it exists. So suppose phi is positive. And being a probability measure will correspond to phi of 1 being 1. Such functional one called states. A state is a positive functional on a C-star algebra which is 1 at 1. Okay, suppose you are given a positive functional on A. So then I want to say that in fact there's more that is true. In fact, phi is a linear functional. A to C linear such that this holds. Then I want to claim that, so the lemma, then automatically phi is bounded. See, positivity already gives you continuity for free. And norm phi equal to phi of 1. Yeah. Sorry? A star means it is a bounded linear functional. Here it is continuous. The continuity is what came for free. I just took a linear functional which satisfied this positivity criterion. And I am concluding that it is automatically continuous. And why is this true? This is true by L2 considerations, like in the commutative case. So what you do is you define this sesquilinear form for x, y, and a. Observe that this is sesquilinear and it is Hermitian. That means b of yx equals b of xy bar. Because if phi sends positive things to positive things in a C-star algebra, then it will be real on real things. And so phi of x star must be phi of x bar. Note that phi positive implies phi of A, the Hermitian part contained in R. This implies that phi of x star by Cartesian decomposition is phi x bar. Consequently, B is Hermitian because B of yx bar will be B of xy. Sesquilinear and positive semidefinite. That just says that B of xx is greater than or equal to 0. And I don't know if I had an opportunity to remark on this before. Usually when you prove the Cauchy-Schwarz inequality, you don't need the fact that you have a genuine positive definite inner product. You just have to have a semi-inner product. That means you must have such an animal. You must have a Hermitian, sesquilinear, positive semi-definite. Then automatically it will be true that B of absolute Cauchy-Schwarz will hold. That is, absolute phi of y star x squared will be less than or equal to phi of x star x power half phi of y star y power half. Then you're taking the semi-inner product is the square root of bxx. Like this is the absolute value of x inner product. No square here. No square. Or let me keep it with the square and without square roots. There is a version that says that the absolute value of the square of the absolute value of the inner product is bounded by the product of the norms. Very good. In particular, this will say that this Cauchy-Schwarz will imply in particular, if I put y equal to 1, it will tell you that absolute phi x squared and now also note that x star x is less than or equal to norm x squared times 1. This is self-adjoint. If any self-adjoint operator will be bounded by its norm times 1, meaning the difference is positive. It comes from the functional calculus. And phi is a positive functional. That means phi preserves order. So phi of x star x will be smaller than or equal to norm x squared times phi 1 whole squared. There are too many squares here, so you throw away the square and you get that phi is bounded and it has norm less than or equal to phi of 1. So you concluded that therefore phi is in A star and norm phi equal to phi of 1. Okay, there is another little fact. I don't think I want to get into the proof of that. You can see the proof in any of these standard books that the converse is true. Phi in A star if phi in A star, then the statement is that phi is positive if and only if so we proved that positive linear functionals, by positive I mean preserving positivity. We proved that the positive functionals satisfy this, they attain the norm at 1. So what one is asserting here is the converse. If a functional attains this norm at 1, then it must be a positive functional. Now given this, it is easy to see that there are lots of positive functions. So for example, let me show you that for each x, let me first consider self-adjoint x. Then by definition, I want to say there exists a phi in A star such that norm phi is 1 and phi of x equals norm x. And the argument is exactly what we did before, because I first look at the C-star algebra generated by x. Look at A0 equals C-star algebra generated by 1 and x. Then this is going to be isomorphic to continuous functions on spectrum of x, with x corresponding to the identity function of the set. This is some subset of the real line. So by exactly what we said before, there will be a point in the spectrum where this attains the maximum, where x hat is x viewed as a function here. There will be a lambda here, so that x hat lambda, mod x hat lambda will be equal to norm x. And then you take that phi naught, you take phi naught as, let us say, evaluation at lambda, where mod x hat lambda equals norm x. And of course, this is evaluation, so this is norm 1. Phi naught of 1 is 1. Now this is actually a complex homomorphism on A naught. But anyway, the linear function of norm 1, that is, which sends x to absolute phi naught x equals norm x. Okay. No, I said absolute value. See, x could have been -1. Then you can't hope to get this if phi is positive. Okay, so now you appeal to Hahn-Banach. You have a linear function on A naught which has norm 1 and it does something on x. By Hahn-Banach, that phi naught can be extended to linear functional phi on all of A, still of norm 1 and still unitl, and doing whatever it did on A naught before. Phi naught as an extension to A with the same norm. that extension phi will satisfy phi 1 equals 1 because 1 is already in A naught. So that phi must be, by this implication, that phi must be a positive functional. Right? So I found a positive functional phi so that this is true. For each self-adjoint x, you can do this, or rather than this, I could have done it for each x in A. I can do it so that I won't say this. Is a phi of x star x equals norm x squared. That is, I'm applying it to x star x, which is already positive, and I don't have to worry about mod or anything. So let me call this phi as phi x. Okay, so no, I should go back to what I do with this construction that we had before. So then let me back up. So I want to look at where the Cauchy-Schwarz inequality without looking at inner product spaces. Let us look at the inner product that we get from the Cauchy-Schwarz. So I define that it's sesquilinear form B. So I say you consider okay, so we already recall, we already defined the sesquilinear form defined by bxy equal to phi of y star x. You know that this is Hermitian, positive, semi-definite, and so on. That means semi-definite means that phi of x star x can be 0 without x being 0. Okay. But now, see, we have this the Schwarz inequality, Cauchy-Schwarz inequality. And we have this phi of y star x, let's say equal to phi of x star x phi of y star y. Now, the next thing is a standard trick that one uses in this kind of business. You say, okay, see, I want to define this as the inner product. Except I can't do that because I will have vectors x for which the thing will be inner product of x with itself will be 0 without x being 0. So one defines the I like to call this the radical of phi, not me, several people do. Then rad phi be all those x in A. That is the problem vectors, the things for which x star x has 0 norm here. And then I see from the Cauchy-Schwarz inequality this implies that if x is in the radical, then y star x is also in the radical for any y. and y star or y or whatever different, because y is completely arbitrary. So this implies that the radical is a left ideal. See, this thing is a quadratic condition. So you straight away look at this, it's not at all obvious that this is a linear vector space. The set of x which satisfy this quadratic condition, it is not clear why x plus y must be there if x and y are there. But now this implies that x and rad phi, or let me put this, I'll put it this way, rad phi can also be written as set of all x such that phi of yx is 0 for all y. Right? If it is a radical, then it certainly satisfies this. If it satisfies this, then for all y, then I can take y equal to x. But now I've reformulated this quadratic condition with a linear framework. That is, I've given a reformulation which is easy to see that this is a linear space. The sums of two things there are there. And that implies that this is a linear space. And in fact, a left ideal I shouldn't have thrown in let me remove that star. Saying all y in A or all y star is the same thing. When you put it this way, it's clear that if x is there, then any zx is also there. So this radical is a left ideal. Okay. Now, the reason why we are doing all this is, it follows that it define let me write x hat equal to x plus rad phi the element of A mod rad phi. I'm just taking this quotient space purely as a vector space. There's nothing algebraic I'm doing. I'm just taking this quotient space as a vector space and defining x hat as the image of x in the quotient. Then one can verify that this B will descend to a genuine inner product on the quotient space. The equation x hat y hat equal to phi of y star x defines yields is a well-defined inner product on A mod rad phi. A mod rad phi contains things like x hat. So why is it well defined? Because this x hat doesn't depend only on x. I could have added something, I could have taken x plus z, where z was the radical phi. These two are the same. Here if I replace x by x plus z, the only difference will be phi of y star z. But z is in the radical, so that is 0. So similarly you must check for y also. So that is why this is well defined. So there is genuine inner product on this quotient space. And further, because it was a lift ideal, we have something good going for us. And what do I want to say? So define, so I claim that there exists. So let me write. So definitely, if we write, we let this is the notation L2 of A phi to be A mod rad phi closure in this, where the norm phi is the norm coming from the inner product, norm of x hat equals phi of x star x square root. There you, the thing that tried to be hello. Now I'm in the middle of a class. Can I call you back in 10 minutes? I'll call you back. Yeah. Yeah. Somebody had taught MSc how many years ago? 30 years ago. More than 30 years ago. 35 years ago. Anyway. So first, I'm constructing something which I want to call this. So this is a Hilbert space, and the assertion is because of the left ideal property, there exists a representation pi. Let me call it pi phi. This is like that pi mu that we defined for Cx. From A to L2 A phi, such that pi phi of x. So it is enough to specify what it does on a dense space. See, things of the form x hat are elements of this dense space of L2. So I define this, so there exists a unique representation pi phi x of y hat equal to xy the whole hat. So this uses the left ideal property. See, left multiplication by things in A, if I say Lx for left multiplication from A, y going to xy. Then because this rad phi was an ideal, left ideal, this would send rad phi into itself. And hence it will map the quotient, it will give you a well-defined mapping of the quotient to the quotient by that first homomorphism theorem or something. If something kills the kernel, then it will give a map on the quotient. So this will give you an L phi tilde, let us say, from A mod rad phi to itself, sending a y hat to xy hat. Right? Y went to xy on top, you can push it down to the quotient, that's what this is. But now, for me to make this Hilbert space statement, this mapping which one has defined only on the dense space must be proved to be continuous with respect to this norm. Right? So there is something we need to verify in order to justify this thing. This requires verifying what? Parveen, please help me. What is the inequality you have to prove now? For me to say that this L phi tilde extends to L phi tilde of x now is a well-defined map on A mod rad phi. What should I do to check that L phi tilde of x extends to a bounded operator on the completion? I have a linear mapping defined on a dense space of Hilbert space. The linear mapping sends y hat to xy the whole hat. I must show that this mapping is what in order to ensure that I can extend it to the completion. You have to show that it is continuous already on the dense space, right? You must show that this is already a bounded linear operator on the dense space. Then it will extend to the completion. Because, right? See, if D is dense in X, you have a mapping from D to D. And you want to say that I can extend that to a continuous mapping from X to X. Now, X has a norm, which also descends to a norm on D. That means my initial map from D to D must have been continuous or bounded with respect to that norm. So we need to check that. We need to check that if you take any norm xy hat, We want to say y hat going to xy hat is bounded. But the norm is the phi norm. We want to say that there is less than some constant times norm of y hat phi norm times some constant. Is that correct? And then we want to say that the thing that sends x to this linear mapping is a representation of A. But if that were the case, then we know that all representations of C-star algebras are contractive. They will all have norm less than or equal to 1. So if this were indeed a representation, it must be the case that, see, this must be pi phi x of y hat. But the norm of pi phi x of y hat, norm of pi phi x is less than or equal to norm x. So you should actually expect, if the theorem you expect is true, then you should actually expect this. This is the norm in A itself. So this is what you need to check. What does that mean? That means you want to say, let's spell it out. You don't know how to compute just the norm in Hilbert space, you only know how to compute the norm squared. What is the norm squared of this thing? So we want to prove this. So the left side is going to be phi of y star x y. Huh? You took xy star xy. You want to prove less than or equal to norm of x squared phi of y star y. This is what you want to prove. But now we've already proved this lemma before. So I define a new map C of Z equal to C of y star z y. Phi. And the point is that phi was positive. That means if I put z equals x star x, this thing will be positive. If I put z equal to x star x, then you have phi of xy the whole star times xy. So the phi positive implies C positive. But C positive implies, what does it say about the norm of C? So this is what we prove. If you have a positive linear functional, it retains the norm at 1, which is equal to phi of y star y. So what do we have here? We have C of x star x, certainly less than or equal to norm C times norm of x squared. But then that is what we wanted to prove. So this proves that the pi phi of x, that we have a mapping pi phi from A to. This proves what we verified is that we're already 5 minutes over. That there exists a mapping from here to here doing this. We still have to verify that this is a representation. That means products, adjoints, and so on. So we'll do that next time, and then we'll